and good evening. My name's Kate Shaw and I'm an experimental particle physicist. So I work here at Sussex with my colleagues and we work with collaborators all over the world, around 3,000 of them. We work on the Large Hadron Collider. Our experiment is one of the 4 experiments there, the Atlas detector. So I also am very passionate about doing outreach. I've been very lucky to be able to take my passion to far corners all around the world. I think it's important that all students, no matter where they are, get access to be able to do research, get access to education, training and mentoring. So I've always wanted to do physics, in fact, since I was about 10 or 11 years old. I even remember the moment. I wasn't necessarily the best at school, but I was a technical child. I liked to take things apart. I grew up in Norfolk, in a very small village, only about 200 people. So there wasn't much to do there, apart from play outside all day and read books. And when I was about 10 or 11, I found a book called The Brief History of Time by Stephen Hawking. You might have heard of it. So this book really blew my mind. I mean, at that age, to understand that we can really understand the universe, we can comprehend it, we can map out how the universe began 13.8 billion years ago. We can tell what happened split seconds after that point. We could understand the geometry of space-time, Einstein's theory of general relativity. We could describe how particles that we can't even see interact in a way that we can't imagine in quantum mechanics. It just blew my mind. And I remember when I finished the last page of that book, I made a dead set decision in my mind that I wanted to be a physicist just like Stephen Hawking. So I work at CERN, as I say, and we do particle physics there. So particle physics is about trying to understand what everything's made out of, but the very, very smallest, like Lego bricks, if you imagine. So we all know that atoms make up almost everything around us, but atoms are made out of electrons, protons and neutrons. Well, protons and neutrons, you might know, are also made out of quarks and gluons. And quarks, gluons and electrons are the fundamental particles. And there's many others, for example, photons, which make up electromagnetic radiation and light. There's also other ones like neutrinos and tau's you might not have heard of. So what we're trying to do, just in chemistry, how we have a periodic table that describes anything you can find in the universe, you can work out what it's made out of a mix of those elements. With the standard model of particle physics, we can tell you what everything's made out of, but the most fundamental building blocks. And we have rules that describe exactly how they behave. We have one of the most precise, or I think the most precise theory that we have in the world that describes fundamental particles. And that's what we do at CERN. This is how we study fundamental particles. So, if you don't know already, the Large Hadron Collider is a particle accelerator, a tube. It's about 27 kilometers in circumference, and it's 100 meters underground near Geneva in Switzerland. And so we put subatomic particles into this tube, and we accelerate them in opposite directions as fast as we can, almost the speed of light, before we smash them together billions of times every second in the center of our big detectors. You can see Atlas here behind me. This is the detector we work on. So every time you have one of these collisions of these subatomic particles, it makes an environment similar to that just after the Big Bang. Okay? That doesn't mean that we're going to make something that's dangerous or has too much energy. It's only an energy density. It's an environment, which means that any particle that was created at the Big Bang, we can create then. And so we can discover everything that happened and all the particles that occurred just split seconds after the Big Bang. And we study them. You might have known the most recent particle we discovered was the Higgs boson, which is responsible for what creates mass. So along with physics, I also acquired another passion. So when I was at university, I had friends that were doing things like geography, politics, anthropology, and I'd really only just read physics up to then, a bit of a sheltered life. But then I got exposed to all these other ideas, and I found it fascinating to learn about world affairs, about different countries, different cultures. It also really fascinated me, and it really gave me wanderlust. And now I get to spend my time actually traveling all around the world, visiting all different types of cultures, and talking to people about physics, talking to physics students. So I really have got the best of both these worlds. So I'd like to tell you how I managed to merge my love for culture and countries with my love for physics. So just after I finished my PhD, I took a few months out to go traveling, and I went around East Africa and around the Middle East. And I was in West Bank, Palestine, and I was just working on a farm for a few days. And I met somebody who knew a physicist that was working at the nearby university, University of Birzeit. And so he put me in contact, and so I went there to give a seminar about LHC and particle physics. And I had a great time. It was wonderful being in somewhere that felt, I hadn't traveled too much before that. It felt so different food, different people. And yet suddenly everything just felt like home. We were all just talking about particle physics. And I enjoyed it so much that after the first year of my postdoc in Italy, just before going to CERN, I went back for 6 months as a visiting lecturer there. And I was still working on the Atlas experiment because I could connect to the internet, so I did all my analysis, but then teaching. And I was really interested to understand the problems that they have there that obviously we don't have here and what we could do to address them. And I'm going to tell you the 3 things that I learned. So it's very important to remember that every culture is different, every country is different. So the list of things will be different for each place, but some are the same. So one of the big issues is that the universities aren't able to do very much research. Okay, there's no PhD programs. The faculty are just expected to teach. If they do any research, it's got to be almost in their spare time. So the faculties that do research are really exceptional. But this is a problem for the students because they don't get exposure to research. They can't get excited about, I went to university in Liverpool where they were working on Atlas experiment. I could see what people were doing. It enthused me, made me think I wanted to get into it. So the second problem they have is isolation. So most universities don't have research in countries all over the world. They may suffer from isolation. But of course, the political issues going on in Palestine just meant that they're super isolated. It was very difficult for scientists to travel. Scientists would not be traveling to go and visit them there. So they were really isolated. They also didn't get funding from the government, from the university to go to conferences. How are they supposed to do research? And the third thing I learned was that the students really had a burning desire to learn about physics. I mean, in places like Palestine and other places in developing countries, if you're lucky enough to get the opportunity to go to university, you're going to be taking medicine, law, engineering, something that leads onto a good job. Although in physics in this country, there's lots of links with industry and lots of good jobs you can go to. We're an attractive breed here. In developing countries, it's not so. But this means that the students that do take physics, there's not many of them, but they are strongly, strongly passionate about it. So when I was there and teaching them and they wanted to know all about the research, it really melted my heart. And I just thought, we're a physics community, we're an international community, we're all over the world. We should come together. What can we do to support each other? Why should some people have access to do research, some people fulfill their dreams, and some people cannot? So I started a program called Physics Without Frontiers. Okay, so the idea is, of course, that no matter where you go in the world, everyone should have education, training, and opportunity to do research. So this was one of the first programs we did in Palestine. This was back in 2012. So the first program we did, myself, and I found obviously I needed more than one person, some Palestinian physicist friends of mine. I managed to find 3. We think the only 3 that existed at the time. And we discussed, okay, what sort of program would be acceptable? What sort of program would work in this sort of place? So we decided, because it's very difficult to travel around, it's best if we went to each university. So we went to each university, we did 1-day training, and they got to analyze data from the LHC. We gave them a big opportunity session. So this is a nice photo for me, because this was one of the first ones we did. This is one of the universities, Al-Quds. And one of the other things we do when we're there is we want to find these special students. There's always at least 1 or 2 in every year within a country who are geniuses, right? Of course there are. And the woman just next to me, she just happens to be right in the middle. I didn't know that she would be there at the time, or who she would become. That's Mezouza. I mean, she was excellent. She answered every question. She was pushing us for complicated questions. And of course, after we left, we continued to mentor her. She went off to do summer school at CERN, did her PhD at Bonn, and now she's a postdoc researcher working on our experiment, on the Atlas experiment. Not only that, but of course now she's joined our network, and now she comes back with us to do training for the next generation. And she's just the first one. This was very successful, and the students wanted more, so we've been going back every year. And every year we get 1, 2, 3, we've been going to Gaza as well, of these top students that just need these opportunities. So, ICTP, which is the International Centre of Theoretical Physics, placed in Italy, Trieste, they made this into an official program. So after a few years of just doing a few bits and bobs, when they could see that if you gave, I mean, these things didn't even cost very much, just a little bit of funding could go so far to changing the lives of these young people. Now we've done, to date, over 30 projects worldwide, from Guatemala to Bhutan. We've been to Nepal, Zimbabwe, Algeria, and we're going to do about 20, we should be doing about 20 or 30 projects this year, and we're hoping to do more next year. So what makes this so successful? We've got so many students, and they're all doing extremely well, and they're all joining our network. One of the reasons is that we make these tailor-made. We can't just make a one-size-fits-all program. Every country is different. For example, we did a program in South Africa. It was to support women. But of course, they have lots of ethnicity divisions there. So you can't, the problems that women encounter in South Africa also depended strongly on ethnicity. And so we had to tailor-make the program working with the people in South Africa to do something that would actually support women properly, rather than only one section. The other reason why we think it's very successful is that it's really leveraging passion. They don't cost very much, it's really just travel budgets, so we can do fundraising for that. But the whole thing runs from the passion of these students and all these wonderful volunteer scientists who are usually from the country and are working abroad. And they're the ones that do it, and they're the ones that run it. So this is not just important to be able to help people like Mazuza and all these other students. It's also important to have science and science research in countries. It helps development. Both developing and developing countries all need scientists. There's an accelerating move to this knowledge-based economy, and you need to have a thriving scientific community to support that, to be able to use the knowledge, to be able to exploit it. So along with supporting these students, we're also trying to support the physics departments there to build up master and PhD programs. It's also important to have scientists in a country for the economy. It increases the scientific capacity the whole way down. Having institutions and lecturers and researchers doing research means that everyone benefits. And finally, it's important for science. We don't know where the next Einstein is going to come from. We want the best people in science, not just the people that happen to be in useful countries that they could get access. So I hope I've convinced you tonight that through using this wonderful passion of physics that all physicists have, we can use it to build a better and brighter future. Thank you.